I'm Alex Paradis, and my presentation is on writing a Python code to solve a given heat transfer problem. The problem statement for this bonus assignment is a brick wall with a thermal diffusivity of 4.72 times 10 to the negative 7 meters squared per second with a thickness of 0.5 meters is initially at a uniform temperature of 300 Kelvin. It is broken up into 3 different parts. These are some of the hints that were given to help in solving this problem. The first hint gives us the information that we will be using the variables dx and dt. The second is to help us in solving for part A, and the last hint is for solving part C. The first thing that I coded were the declarations. These are Python packages that are imported and allow you to use special features that you would otherwise not be able to do if they weren't imported. NumPy is imported in because it allows you to create arrays that can be used in mathematical functions. It is abbreviated as NP so that it will take up less space in the code. We then import matplotlib.pyplot as this will allow us to graph our data. It is also abbreviated to simplify the code. The next step is initializing the variables given in the problem statement. I inputted the givens into Python and added dx, dt, and k into it. The bottom 3 lines of code are variables that were not given and that I had to come up with. The dx is the change in length going into the wall, the dt is the change in time, and k is a variable that was given as a hint that will be used later on in the code. The next step is setting up the first part of the body. We need to make arrays because they assist in storing multiple sets of data and make it easier to call them later in the code. One of these arrays, first T, is for the starting temperature against the wall. The next array, next T, is for storing the temperature across the length of the wall at their respective time. And the last array, wall, is for the different values of the x across the entire length of the wall, which is given by the dx value. I made n equal to 300 so that it would simplify and shorten the code. This step involves making while loops and incorporating the equation given to solve this problem. We start with creating the variables first time and counter. We then create our first loop, which sets the loop to end when T is no longer less than or equal to 425 Kelvin. The next loop calculates the temperature at the next time interval, and the final loop sets the starting temperature to be equal to the next T. So, when the loop starts over, it can begin with the next value. The counter is set to keep track of the number of iterations to use in the final equation, and the last 2 equations solve for the amount of time, and we end up finding that our answer is 16.8 hours. For part B of this problem, we needed to plot the temperature change over time. This was done by using the code plt.plot wall next t, which plots the arrays of the wall and next t against each other. The following lines of code display the graph and add a grid to it, while the previous lines of code create the fonts and titles for the graph. I am now going to run the code for you. As you can see, 16.8 hours, and the graph is plotted. For part C, we had to solve for the stability criteria for a 2D and 3D system and explain why it looks that way. The stability criteria for a 2-dimensional heat transfer system should look like this equation, because when the coefficient of this is set equal to 0, it then becomes this equation. This is the stability criteria. It's the same process for a 3-dimensional system. However, the denominator is 6 instead of 4 because it is three-dimensional. These equations were pulled from the Heat and Mass Transfer Fundamentals and Applications textbook that is used in class. The sources that were utilized in this problem was W3 Schools for Python and Heat and Mass Transfer Fundamentals and Applications for equations.